Okay, the last topic that I want to talk about in this chapter is thin film interference. And it's another interference effect, similar to the diffraction effects we've been talking about, where we're talking about sources of light, two different sources combining in interesting ways. And so that's what it has in common with all of the effects we've talked about in this chapter. The basic idea is shown here. We see here a candle. This is the source of light, and it's reflecting off of the front surface of this mirror and the back surface of this mirror. Now, a mirror is typically a sheet of glass, and one side has been silvered. It's been coated with some highly reflective metal. In the old days, they used silver. I don't know what they use nowadays, but some kind of highly reflective metal. And so you actually can get a reflection off of that front surface of glass as well as the back surface of glass. Now, you all have actually probably seen this. If you've got one of these rear view mirrors with the little tab on it that can switch between daytime driving and nighttime driving, then that's exactly what you're seeing. When you have it in the nighttime position, then you're catching the reflection off of the front of the glass, which is much weaker, and so it's appropriate for cars with bright headlights that are behind you. But if you switch it to daytime driving, you're catching the reflection off the back side of the glass, which is a stronger reflection and more appropriate for daytime driving. That's exactly what we're seeing here, except we're seeing both reflections at once. Now, if the reflections are combining off of two surfaces, and those surfaces are separated by a large distance, and by large I mean large compared to the wavelength of light, as shown in this slide here, then we'll just see two images. We don't get these interesting interference effects unless that surface is very small. And what do I mean by small? I mean of the same order of magnitude size as the wavelength of light that's interacting with it. When that happens, we get very interesting wave interference effects. And that's what we're talking about when we talk about thin film interference. And you've seen this before too, actually. Let me jump ahead just a couple of slides and I'll show you what we're talking about. Here is an example of some thin films. Here we see this is a thin air layer in between two plates of glass. And so, again, what we're seeing here is light combining from the top surface of the bottom piece of glass and light reflecting off of the bottom surface of the top piece of glass. Again, there's a thin layer of air in between two glass plates. And we see some really interesting effects. We'll come back to this slide in just a second, but this is in a larger sense, this is what we're talking about. Let's see how this happens. The basic idea is you get some wave coming into this. The basic idea is anytime you have a wave that is incident on some boundary, then you get two waves. You get a transmitted wave and you get a reflected wave. So it always splits, and we see evidence of that in this picture too, right? This front surface has definitely reflected a little candle back at us. Some of the light passed through and reflected off of the back surface. So we're seeing evidence here of some of the light being transmitted and some of the light being reflected. Now there's two different cases here. In one case we might have a phase change, in another case we will not have a phase change. And the basic idea with a phase change is that the wave gets flipped upside down. And so this is a little bit of a difficult thing to demonstrate here in the video. So I'll have to draw you a picture. So let's say that I have a rope and it's tied to a wall. And I send in a wave pulse. Right? And so I send in a wave pulse, and let's say that the wave pulse is shaped like this, okay? So here's my hand over here. Hand shaking the rope. And I sent this wave pulse in, excuse me, and it's headed in this direction. So there's the velocity of my wave pulse. Well, when it hits this boundary, it's going to reflect off. And so when it hits this boundary, it's going to reflect off. And it's going to head back in this direction. But what's really interesting here is it won't just head back in this direction as it was. And we'll draw the reflected pulse in orange here. The reflected pulse actually will invert. It dips down. This is called a phase change. So this is what I'm talking about, a phase change. This is an example of a phase change. When this particular wave, and here I'm talking about a wave on a string, and the waves that I'm talking about in this lecture are light waves, but it's the same exact idea. When this wave bounces off of this barrier, this boundary, if you will, it reflects back this way. The reflected wave is inverted. We call that a phase change. And what it does, in effect, is it shifts the outgoing wave by a half of a wavelength. Let's see what I mean by that. Looking back at the PowerPoint, now in this example, what I demonstrated was just a single pulse because it's easier to see. But we know that if we're talking about a light beam, you know, a laser, for example, laser, I don't know if you can see that, then we're talking about a steady stream of waves. And so it's more like a sine wave. And so looking back at this slide, here's our incident wave. The transmitted wave just keeps going, and notice it's continuous here, right? It's just no phase change, nothing weird. This one just continues right through the boundary. This one right here, though, it reflects off. Now, notice it does not have a phase change. How can I tell? It did not flip upside down. Notice it's still aligned with the incident wave. The peak aligns with the peak, the trough aligns with the trough, the peak aligns with the peak. So the reflected wave is in phase with the incident wave. In this case, the reflected wave is not in phase with the incident wave. Notice it is upside down, and it's really easy to compare these two. Here we have a peak, here we have a trough, here we have a trough, here we have a peak, here we have a trough, here we have a peak, right? So these are inverted because this has undergone a phase change. Now, when do you get a phase change if we're talking about light waves? We get a phase change when the light is bouncing off of a boundary where you are going low N to high N. So notice here is N1, here is N2. If N1 is greater than N2, we're reflecting off of a phase change from high N to low N. If you're reflecting off of a boundary from high to low, you do not have a phase change. If, however, N1 is less than N2, this side has a greater N than this does. Now we are reflecting off of a boundary going low to high. There is a phase change. Okay, so that's the first thing we have to wrap our brain around in order to get through the problem-solving strategy of thin films, okay? So now we're ready to see how this phenomena happens. We get some, here we have a thin film with some index N, and it's on top of glass. A lot of eyeglasses have a thin film anti-reflection coating. So this might be a demonstration of that. This is what that might look like. Here we see light coming in through air, and it interacts with this thin film and then passes on through the glass. So here we're looking at the transmitted wave. But we know that some of it reflects, right? So we get a reflection off of the front surface, and we get a reflection off of the back surface. That's what we're talking about. And when I'm looking at these pretty colors here in this picture, what I'm looking at there is the combination of the waves reflecting off of one side of the thin film and the other side of the thin film. And again, here we're shown two reflected waves. And here they're overlapping in a way that is not completely constructive and not completely destructive. It's drawn that way so that we can see it. And really, for most wavelengths, in most situations, this will be the case. As with a lot of problems in this class, we'll constrain it. And I'm only going to ask you about situations when they are completely in phase or completely out of phase. That's when we get really interesting effects. For example, right here, where we see this beautiful green color right here, for this green color right here, that is because for that wavelength of light, for that green wavelength of light, the reflection off of the top surface of this bubble of soap and the back surface of the bubble of the soap, so those two reflections are combining in phase for that particular wavelength. And so I see this nice bright green color. They're out of phase or not perfectly in phase for all the other colors, so I don't see those, right? What stands out to me is that pretty green color. Similarly, there's this lovely magenta right here. Again, for that particular wavelength, with that geometry of that soap bubble, the light from the top of the soap bubble and the light from the back of the soap bubble are interfering. Now, be careful. I'm not talking about the whole bubble, right? I'm talking about just this very, very thin film. This is just this thin film of soap, right? So it's a reflection off of the top and the back side of the thin film. It's not one side of the bubble interfering with the other side of the bubble. There's air in between. That's huge. It's large compared to the wavelength of light. We're not going to get these effects there. It's both sides of the bubble. Okay, so if the two reflected waves are in phase, we get a strong reflection, and that is constructive interference, and we see a strong reflection at that wavelength. However, if the two reflected waves are perfectly out of phase, then we end up with destructive interference, and we will see a dark color or something that's just not bright. And much like a lot of these effects, or all of the effects that we've been talking about in this whole chapter, it really comes down to the fact that the two waves that are interfering, the two reflected waves that are interfering, they travel different distances to get to some location. So, for example, to get to right here, the one wave had to go all the way through this thin film and then back out, whereas the other wave came in and reflected off the front surface and back out. Again, one wave went in, reflected off the back surface and came out. One wave came in, reflected off the front surface and came out. The wave that reflected off of this surface simply traveled farther. And much like in a lot of this stuff, we get a path length difference. And when that path length difference is equal to an integer number of wavelengths, we get constructive interference. When it's an integer plus a half number of wavelengths, we get destructive interference. And we see here that if T is the thickness of our film, then the wave that reflected off the back surface traveled twice through that thin film, and so the path length difference is 2 times the thickness of the film. Okay, again, we get these beautiful colors. This is an air layer between two plates of glass. This is a layer of soap between two layers of air. And here we see a thin film of oil sandwiched between air on top and water on the bottom. Okay, so let's just look at this first equation. There's this chart with the 4 equations, and we'll go through exactly how to work your way through this chart. But first, let's just talk about this first equation. We're talking about constructive interference in 0 or 2 phase changes. So we'll come back to what that means, 0 and 2 phase changes. We've kind of talked about it, but we'll talk about the problem-solving strategy here. So for constructive, of course, constructive interference happens when the path length difference is equal to an integer number of wavelengths. It turns out that that's exactly what this equation says. What is 2t? Well, that is the path length difference. So 2t is the path length difference. M is an integer. What is lambda over n? Well, lambda divided by n is the wavelength in the film. Right? So lambda is the wavelength in a vacuum. And earlier in this chapter, we learned that when light moves into a different medium, it's the wavelengths that get shorter. So lambda divided by n is the wavelength in that thin film. So notice we can read this equation just like a sentence. The path length difference is equal to an integer number of wavelengths. That's what we're saying, right? So now notice, go back here to destructive. The path length difference is an integer plus a half number of wavelengths. That's exactly what that says too. Okay, so there we go. We need to know whether we're looking for constructive or destructive. Clues to destructive or constructive are things like, hey, I see a bright green color. Okay, well, that's telling you that green is in phase or constructive because it's bright. I could say an anti-reflection coating. Ooh, anti-reflection. Anti-reflection. That's destructive. I want to cancel the reflection. Okay, so those are clues that you're going to look at. But again, I see a bright color or a strong reflection for constructive, and I see no reflection for destructive. It's some very, very interesting physics that has a lot of applications. Now, we just need to now decide how many phase changes are there. And let's go back up to this picture that we had right here. Remember, we've got a wave bouncing off of this surface interfering with a wave bouncing off of this surface. We just need to decide, do we have a phase change here? Do we have a phase change here? So there's a possibility of 0 phase changes, 1 phase change, or 2 phase changes. If there's 1 phase change, it basically adds 1/2 of a wavelength to the reflected wave. And so that's why the equations kind of switch if we have 1 phase change. But if you get 2 phase changes, it's like adding a whole wavelength to the reflected wave, and we're back where we started. So again, we identify, are we constructive or destructive? The wording of the problem will tell you that. You need to draw yourself a quick picture, and that will help you decide whether you have 0, 1, or 2 phase changes, and then you pick out the equation and you roll with it. Okay? I have a quick example, a quick clicker question example here. So here we have a film with a thickness T that gives constructive interference for light with a wavelength in the film of lambda film. Okay? Again, remember that this is the wavelength in a vacuum. This is wavelength in a vacuum. Lambda over n is our wavelength in the film. So we've got a wavelength in the film of lambda film. How much thicker would the film need to be in order to give destructive interference? It is constructive. We're going to make the film a little thicker in order to make it destructive. Why don't you pause the video and see if you can figure this one out. You're going to probably need a picture. Okay, well, let's look at this. Here I've drawn this picture. Again, we've got constructive. We want to make T a little thicker in order to change it into destructive. What's that going to look like? Well, so we've got our incident light that comes in. One ray bounces off of there, and another ray bounces off of there, and then they combine, right? The path length difference in this case is equal to an integer number of wavelengths because they told us it's constructive. So here we have 2t equals m lambda film. What we want to change this to is 2t equals m plus 1/2 times lambda film. Right? So what we need to do is we need to add 1/2 of a wavelength. And, you know, we could maybe do a quick piece of algebra here to show that that's for sure true. This ends up being m lambda film plus 1/2 lambda film. Okay, so we need to add 1/2 of a wavelength. Well, how can we do that? We need to add just a little bit here. And what is that? Well, our wavelength now, our second reflected wave now has to go here and back. So this is what I'm adding. Notice that I'm adding, the light has to go twice through this, right? And so in order to have a total path length difference of 1/2 lambda film, this right here has to be 1/4 of a wavelength. So we add 1/4 of a lambda film. That way I get a quarter here, a quarter here. I added a total of 1/2 of a lambda film. Let's see if PowerPoint agrees. And it does. Oh, goody. So we have to add 1/4 of a wavelength. That's a little bit of a tricky one. But I think it's good because it gets us thinking about this path length difference and how we shift from constructive interference to destructive interference. Okay, here's another example. To keep unwanted light from reflecting off of the surface of eyeglasses or other lenses, a thin film of material with an index of refraction of 1.38 is coated onto the thin plastic lens. What is the thinnest film that will minimize reflection for lambda equals 550 nanometers? Why don't you go ahead and pause the video and see how far you can get with this, and if you get stuck, hit go until you get unstuck, and then pause it again, and let's see how far you can make it on your own. Okay, so the first thing we should do is draw our picture. So here we have air, which is N equals 1. And then we have thin layer of a material with index of refraction N equals 1.38. So this is our film right here. And then we have the plastic lens, which is N equals 1.55. Okay, so here we have the air, film, lens. Okay, air, film, lens. Great. So what we need to do is we need to decide where on this chart we are. Do we have constructive, destructive, 0 two-phase changes, or 1 phase change? Okay, well, let's look at this. We have light coming in from here. Some of it bounces off of there, some of it bounces off of there, and then it combines out here. So that's what we're talking about. Is there a phase change right here? Well, we're going from low N to high N. So, yes, there is a phase change. Is there a phase change right here? Well, we are going from low N to high N. Yes. So, that means we have two phase changes. Now, are we looking for destructive or constructive? Let's look back at the language of the problem. It says, what is the thinnest film that will minimize reflection? Constructive or destructive? It is destructive. We're looking for destructive interference. So, now we've decided where on this chart we are. We are 2 phase changes, destructive. This is the equation we want to use right here. Great. And it gave us a lambda of 550 nanometers. Let's write that down. Okay, so now we're ready to just do our algebra. Let's do it. So we're looking for the thinnest film possible. So M, what's the smallest then that T can be? Well, that's when M is the smallest it can be. So M equals 0 for thinnest. Which means that we end up with 2T equals 1/2 lambda over N. And so now we can solve for T, and we get lambda over 4N, and now I can plug in. Now, which of our N's are we going to use here? Because as you can see, we've got 3 different N's. It's always the N of the thin film. Remember, we can read this like an equation. Read this like a sentence. The path length difference is an integer plus a half number of wavelengths. Wavelengths where? Wavelengths in the thin film. Right? Remember, lambda is always lambda wavelength in a vacuum. Lambda over n is the wavelength in the film. Therefore, we put 1.38. And we get a number, and that number is about 100 nanometers. Okay. So this happens in animals all the time. Lots of animals have structural color. And so we kind of started off this chapter talking about structural color from a hummingbird. It turns out that that is reflection grading, physics, essentially. But we can also get structural color from thin films. Here is an abalone shell, which you can see has these beautiful rings of blue and yellow. In fact, if you chip these flakes out, they are very thin stacks, and these colors come from reflections from the top and bottom plates of those stacks. They're not actually purple or blue or bluish green, whatever color those are. They're actually clear, and it's the reflection, the way the light reflects off of them, that gives them the color. It's not pigments that are giving them the color. It's structural. It's structure that's giving it the color. I'm going to ask you a question on the homework about an octopus that's very similar. An octopus also has some structural color in it. Here we see a picture of a soap, thin film of soap between two layers of air. So why do the colors shift as you move down the film? And why is there no reflection at all at the top? Well, I think in order to wrap our brain around this, we need to think about, what is the thickness of the bubble uniform? And it's not, right? This is the top of the bubble, or of the film of soap, I should say, and this is the bottom of the film of soap, which means that this bottom part is actually thicker than the top part. So the top part is so thin that the strong reflections are in wavelengths that our eyes can't see. And so we're seeing no strong reflection off of the top because that thin film is so thin that any light that is reflected is shorter wavelengths than our eye can see. And so, of course, red is the longer wavelengths, blue are the shorter wavelengths. And so right here at the top, we just see a hint of blue, the very shortest wavelengths that are visible, starting to add constructively. So right in here, this is constructive interference for blue wavelengths, which are the shortest wavelengths that you and I can see. And then we see up to some nice reds right in here. So this would be blue to red, one wavelength fitting in that thin film. And then we see blue to red, two wavelengths fitting. Three wavelengths, 4, 5, I might have lost count in there. As you get up into here, we start seeing many wavelengths fitting, and we start to not see quite as crisp of a pattern. These interference effects go away as the thickness of the film gets larger than the wavelengths of light that we're talking